Kelvin body force. So essentially what you do is you set up a magnetic field with diverging flux lines, and you can make that magnetic field using a dipole or an electromagnet. And so there are various ways of generating these magnetic fields. And once you generate this magnetic field, you can then essentially start to look at the application. So if you look at just a conduction profile in that example that I showed you, which is hot on one side and cool on the other side, you'll basically see a diffusion layer in the sense that heat will just conduct, it will just diffuse. It's a conduction problem. But one of the properties of ferrofluids is that their susceptibility to a magnetic field is high when they are cold. Their susceptibility to a magnetic field is low when they are hot. So using temperature, you can tune the susceptibility of the ferrofluid to the magnetic field. And when you do that, if you look at a hot and a cold location, firstly, you have the diverging flux line. So you have the gradient of the magnetic field. And then, of course, you have the gradient of the susceptibility from point 1 to point 2. And then you use these effects essentially to drive a flow. And you can then start to get a convection pattern that mimics that of natural convection. So here I've shown you an example that by going to the microscale, instead of getting natural convection, you can get something very similar to natural convection. The same kind of vorticity, the same kind of cavity-driven flow that you would get with natural convection, but at the microscale, substituting natural convection for thermomagnetic convection. All right, so the magnetic phenomena is very similar to the natural convection phenomena. When you look at natural convection, you basically map the heat transfer essentially through some kind of a characteristic parameter like the Nusselt number with the Rayleigh number. In fact, when you use the magnetic parameters, you can come up with a similar number, which is the magnetic Rayleigh number, and the behavior of the heat transfer, the Nusselt number versus the magnetic Rayleigh number relationship is essentially identical. You can not only look at heat transfer with fluids, with magnetic fluids, with a natural convection analogy, you can also enhance heat transfer in microscale channels using a forced flow analogy. Here what you simply do is that when you apply a magnetic field, you agglomerate the magnetic fluid. When you agglomerate the magnetic fluid, it forms a step. It's basically a hot fluid flowing over a step. When it flows over the step, it causes a certain amount of recirculation. You know that when you have recirculation, when you have a hot fluid with cold walls and so on and so forth, you will have heat transfer, and so that's how you accomplish the heat transfer. So very, very simple analogies to what you actually study probably in a junior level or a senior level undergraduate mechanical engineering course. You can vary the dipole strength in the case of forced flow and tune the Nusselt number to whatever you wanted for that particular application. So there are other strategies. So this is a patent that I have with some of my students. This work has now been taken to India. I have a student who's a professor at Jadavpur University who's developing a thermomagnetic pump for the institution in India called the Bhabha Atomic Research Center. This is a nuclear research center. It's worked on in nuclear reactors. And so the whole idea in a nuclear reactor is how do you get pumping in a highly radioactive environment without using any moving parts. Why don't you want moving parts? Because moving parts can fail. When they fail, then you have to go in and extract those parts. You have to deal with them. You have a certain downtime in a nuclear reactor. But if you can, based on the simple principles that I showed you earlier, if you can design a thermomagnetic pump, then you can essentially drive a flow which essentially accomplishes heat transfer. Now I want to be very clear. This is not sort of a chicken in every pot or a Mercedes in every garage. You've got to be very careful when you use magnetic fluids. You can use them when you want to cool or heat microscale applications. If you really want to cool spaces of this dimension, it's really not an option. So we've got to be very careful about where the window of application or the window of opportunity is for this particular application. We'll talk a little bit about MEMS devices. Some of the work that we've done is in developing switches and in developing lithography techniques. So I'll refer to them later. But before I do, let's talk a little bit about another application, and we'll call this dynamic self-assembly. So dynamic self-assembly is that when you have two competing forces, you can take a dominant force and create a structure. When you release that force, that structure will dissipate. So that's the basic principle of dynamic self-assembly. So you can use magnetic fluids to form simple structures. So these are simple structures that are formed in my laboratory. You can tune those simple structures by tuning the magnetic field. You can form semi-permanent structures. So if you take the ferrofluid and form these semi-permanent structures, and you put a coating on these, that coating is essentially just epoxy. The epoxy is just the whiteout that you have, that you can use. And when the epoxy cures, you now have a semi-permanent structure. So there are applications of this to form on-demand rough surfaces. You can form on-demand rough surfaces for certain applications. Remember that step that I showed you in the forced convection application? You can form a step, you can take the step away. So you form on-demand structures, and then when you don't need the roughness, you don't need the structure, you can essentially wipe it away. So here's another self-assembly application that we developed for basically manipulating micro devices. In this case, this was a catheter. When a surgeon or a cardiovascular physician puts a catheter or a device to do some procedure, it could be essentially an angioplasty, for instance, or any other procedure. They have a camera at the end of the catheter when they work the catheter through your artery, or as you get older, you'll find that there are gastrointestinal experts who work catheters in interesting ways through your body. When you have colonoscopies and procedures such as that, at that point, you really don't want the physician who's doing the cardiovascular angioplasty to puncture any of your arteries. Neither do you want the gastroenterologist to rupture your colon in any way, right? So it's very important to give them line of sight. That line of sight is sometimes difficult. These procedures are very difficult for any of you who've seen them. And so this is a very simple way of putting a mirror at the end of the catheter and maneuvering the mirror by essentially using the dynamic self-assembly concept that I showed you earlier in order to raise the mirror, angle it, or change it in other ways. Here's an example of a MEMS switch. You essentially have two electrodes. You apply a magnetic field and you close the switch. Ferrofluids can be conducting. You can choose the right host fluid. The nanoparticles are conducting because they're essentially ferrous. They're iron-based. So you can close a switch, you can open a switch, and so essentially it's action from a distance. You don't have to have electrostatic fields. You don't have to have any moving parts. So really the theme here is action at distance. All right. This is the etching application that I talked to you about. Here what you essentially do is that if you have a template and if you'd like to etch a microchannel in a certain substrate, what you do is you take the etchant and you mix it with a ferrofluid, you have a flow, and then essentially what you do is you tune your magnetic field to where the flow should go. The ferrofluid carries the etchant, and when it carries the etchant, it essentially etches out the channel or the dimensions that you want. Why is this advantageous? Because conventional techniques will essentially give you straight lines. Conventional techniques will give you essentially uniform cross-section. But here, by tuning the flow, you have the ability to develop curve geometry, and you have an ability to develop